In each of these examples, we are being asked to rewrite a formula to isolate a variable that has been squared. For right now, we're going to assume that the variable being squared is something where what's plugged in is greater than 0, so something positive. We'll talk about the meaning of that shortly. Now later on, we might wish to apply something like factoring or completing the square or the quadratic formula to help in writing similar formulas to isolate a variable that's been squared. But for right now, all we need is the square root property. And so we need to take a look at what has happened to the variable. In this first one, solving for r, after the squaring part, all that happened was that we added 1, and so we shall subtract the 1 to get r squared alone, followed by taking the square root of both sides, canceling the square root on the left, and we've got r is equal to plus or minus the square root of s squared minus 1. Now, for one thing, we were told to assume that what we're plugging in is greater than 0, so this is going to be something positive. We could worry a little bit about some values that would still make what's under the square root negative and not give us a real number, but what we're talking about here, assuming that what's plugged in for s or for r is positive, specifically for r, means we can drop out that plus minus part and just talk about the principal square root. Something to watch out for, you cannot simplify that any further. Although there is a product rule and a quotient rule for splitting up square roots, there is not one for adding or subtracting. If s was 3, and you thought that you could split up that square root, well, here you get 3 squared is 9, 9 minus 1 is 8, and that would be approximately 2.8. And over here, if we could split up subtraction that's under a square root, we'd have the squaring canceling the square root, or vice versa. Square root of 1 is 1, 3 minus 1 is 2. We're not getting the same thing. These are not the same. We cannot split up that subtraction, and something similar will come up in the next problem. So here we're supposed to solve for n. After the squaring, all that happened was we subtracted 4p squared. So I'm going to add 4p squared. To the 9q squared. Take the square root of both sides so that it cancels on the left, cancels the squaring. And again, since we're assuming that what's going in for n is greater than 0, we'll just take the principal square root and drop the minus part here. Same thing, we've got addition here. We're not going to be able to simplify what's under that square root. And for the third example, to solve this for c, after squaring c, the only thing that happened was it was multiplied by b. So I'm going to divide both sides by b. If you'd prefer to see the c squared on the left side. x equals y, y equals x also. Take that principal square root. Oh, cancels on the left. We only want the principal square root. And since it's division, we can split that up, but we don't want to leave a square root in a denominator. So I'm going to multiply top and bottom by the square root of b to the first. In other words, I'm squaring square root of b in the denominator to just get b, and I'll put back together these two. The reason I'm doing that, I'm allowed to do it because of the product rule for radicals, but also the power of either variable is not bigger than 1. The index is 2, the powers are less than that, and so they're going to stay underneath a square root.